Good day everyone. So the problem given to me is to describe the relationship between operators and observables in quantum mechanics. Now before I explain the relationship between the two, let me first explain what is an operator and what is an observable. So first is, what is an operator? Operators carries out a mathematical operation on a function, or it is a mathematical entity that acts on a function which gives us a measurement. For example, we have this eigenvalue equation. A hat times psi of x is equal to phi of x. Mathematically, if we have a function psi of x and an operator a hat, when an operator a hat acts upon this function, we get another function phi of x. So basically, when an operator acts on a function, it produces another function, but the function is still the same, which is x. This eigenvalue equation can be written as the operator times a function is equal to a constant factor times the same function. Let's take, for example, the operator form of the Schrödinger equation. The factor e is called the eigenvalue of the operator. When you say eigenvalue, it's just some constant factor of the operator, which in this case is E, or the energy. The function phi in an equation of this kind is called an eigenfunction. It is the eigenfunction of the operator, and this differs for each eigenvalue. So therefore, we can rewrite this general form of the equation as the operator times the eigenfunction, which is equal to the eigenvalue times the eigenfunction. Because this is a Schrödinger equation, the eigenfunction in this case is the wave function corresponding to the energy E. Moving on to the next. So now, what are observables? Observables are any measurable properties of a system, like momentum, electric dipole moment, or energy, and so on. So basically, when you say an observable, it is something measurable. It is a measurable quantity of quantum mechanics. Now, what is the relationship between these two, the operators and the observables? The importance of eigenvalue equations is that the pattern exemplified by the Schrödinger equation is repeated for other observables. Thus, it is often the case that we can write this general eigenvalue equation: operator corresponding to an observable times the wave function is equal to the value of an observable times the wave function. So once again, let's take a look at the operator form of the Schrödinger equation. So the symbol h hat, or the Hamiltonian operator, corresponds to a certain observable, which in this case is energy. And the eigenvalue E, or energy, is the value of that observable. Therefore, if we know both the wave function and the operator corresponding to the observable of interest, and if we also know that the wave function is an eigenfunction of the operator, then we can predict the outcome of an observation of the property by picking out the factor in the eigenvalue equation, for example, an atom's energy. The basic postulate of quantum mechanics tells us how to set up the operator corresponding to a given observable. Observables are represented by operators built from the following position and momentum operators. So for each observable property of a system, there is a corresponding operator built from the following position and linear momentum operators. So x hat is equals to x is the position operator or x hat times a function equals x times a function. And for the linear momentum operator, p hat equals to h bar over I times the first derivative with respect to x. The operator for location along the x-axis is multiplication of the wave function by x. And the operator for the linear momentum part is parallel to the x-axis, is proportional to taking the derivative of the wave function with respect to x. Thank you so much for watching.